Hi everyone! In this video we're going to continue talking about vector fields and line integrals. We're going to get a little bit more specific though. In the last video we talked about what is a vector field and we talked about evaluating line integrals of vector fields. Now we're going to talk about work, circulation, and flux. So let me start with work. So the work done by a force over a curve in space. So here's the definition for this. First, we're going to let F, capital F, be a continuous force field. In other words, that's our vector field. In a region containing C. So we're using capital C as our curve. So it's a smooth curve, which is parameterized, and we're reserving R of T for our parameterization. That's how we're going to label our curve, and it's from T is A to B. So by definition, the work done in moving an object along this curve C in the forward or positive direction, the work done by this force field or vector field in moving an object along a curve is this line integral. And so we've seen this previously, we're just now labeling this or calling this work by definition. And so I'm giving you actually four different versions of the same integral, and it's because it's easier to evaluate most of the time using different ones here, and I'll point them out. So W for work equals our line integral of our force field dotted with T, the unit tangent vector, with respect to S, where S would be our arc length. This is the integral over our curve C. So a lot of times that's not the easiest version to use. Rather, we use this one. And so this one, and we'll do an example. We're going to evaluate our force field at our parameterized curve, R of T. We're going to dot that with the derivative of that curve, so the derivative of R with respect to T, and then we evaluate that integral from A to B. You can also write the same thing in a couple of other versions. In the previous video, we saw if we wanted to look at just specific directions, so like the X direction, Y direction, Z direction, how we could take each individual line integral, and this is just a combination of the three of them. So the integral over our curve C of m dx plus n dy plus p dz. So previously, where these letters come from, we defined our vector field, or in this case we're calling it a force field, as our field F equals m I for the I direction of our vector plus nj for the j direction of our vector plus pk for the k direction of our vector. So that's where m, n, and p came from. I'll just write that really quick here so you don't have to just hear me say it. It was mi plus nj plus pk. And that's our force field or vector field. And then down here, you can rewrite this in terms of t, the parameter t, just like we do back here. If you say m times g prime of t, so basically the dx is getting replaced with g prime of t dt, and then very similarly for dy and dz. So the g, the h, and the k, we talked about it previously, those all came from our curve. So our curve, I'll write that here as well. We had r of t was g of ti plus h of tj plus, and this one's a little silly, but it's k of tk. So let me just put my vector notation on. That's the vector component k. This is just a function called k. So that's where these labels came from, just so you're aware. We went over them in the previous video. So by definition, this is going to be how we calculate work. So let me show you just an image of this real quick. Okay, so the blue curve here is our curve C, and we have this force vector that is from our vector field, and then our unit tangent vector is going to be tangent to our curve at this point, and then it points in the direction of travel. And so the work done by this force F is equal to our line integral of F dot T from the starting point to the ending point. Alright, so just a quick note, If the curve is traversed in the reverse direction, so we have what would be defined as a positive or forward direction. If your object is traversing your curve the opposite direction, the opposite way, then you just evaluate your line integral, you could say over the opposite direction of your orientation here, but it just becomes negative of your original integral. So just be aware of that. It has to do with the orientation of your object traveling on your curve. So let me give you some common parameterizations. You might remember these from learning them previously, but if a lot of times you're going to be given a parameterized curve, but not always. So let me just sort of remind you a little bit about maybe what you know for parameterizing a curve. So one thing is a line segment. So let's say our curve is a line segment, we'll say through some given point, I'll call it AB, and then we know maybe another point on the line segment or the slope of the line, so I'll just say with slope M. Then you can parameterize this path, this curve, as x equals a plus t, y equals b plus mt, and then t, we'll just say goes from t1 to t2. Whatever these t values are to get you from your starting point to your ending point. So just a common parameterization for a line segment path. Another one is a circle. So let's say your path is a circle and you know the radius. So I'll say with radius a. A common parameterization for this would be x equals a cosine t, y equals a sine t. And if you're traversing the whole circle, t is going to go from 0 to 2 pi. So if you know your path is a circle, you can use this parameterization. And then I'll just say in general, this is the natural parameterization. So if you're not sure how to parameterize a curve, you can always try this. You can always just say that you're going to let x equal your parameter t, and then let's say you know some function describing your path, it's just maybe not parameterized with t. You could just say that y equals like f of t. So x is just t, you replace x with t, and then you plug in t into your function to get y, and then same thing, you have some interval for t. Okay, so just sort of reminding you a little bit about parameterizing a curve, because you have to do that in order to evaluate our work line integrals. So let me go ahead and go right into an example now where we calculate the work. Okay, here's this example. Find the work done by the force field given here, F equals y minus x squared I plus z minus y squared j plus x minus z squared k. So the work done by this force field in moving an object along this curve. R of t is ti plus t squared j plus t cubed k. And we're moving this object from the origin to the point 1, 1, 1 in space. So the process is really similar to the line integrals we evaluated for vector fields in the previous video. So we're going to go through our steps for this one. So I'm going to start with finding our force field evaluated at our curve r of t. So we have f of r of t. So let me just sort of label a little bit real quick. From our curve, the x here would be t. Y would be t squared. And then z would be t cubed. So we're just plugging that in to f, our force field here. So f of r of t is y, which was t squared, minus x squared, which is t quantity squared. And that's our I component. Next, for the j component, we have z, which is t cubed, minus y squared, which is t squared quantity squared. Then last, our k component over here, we have x, which is just t, minus what was z squared, but z is t cubed. So t cubed quantity squared for k. Okay, so let's just make this look a little bit better real quick. We're going to get a t, this one's 0 actually, so I'm not even going to write that out. 0 in the I direction. Right here in the middle, this becomes t cubed minus t to the 4th, j. And then in the back over here, this is just t minus t to the 6th for k. Alright, so that one's done. The next thing we need, because it's going to be part of our integral, is the derivative of our path or curve, r. So find dr dt, derivative of r with respect to t. So dr dt, if we just look at our curve over here, just take the derivative with respect to t. So the derivative of t is 1, so 1i, t squared becomes 2t for j, and then t cubed becomes 3t squared k. Alright, now if you look back at our integrand, we need f dot dr. So next we're going to find the dot product of these two. So let me erase part of this. I'm going to go ahead and leave from the origin to 1, 1, 1 because we didn't actually do anything with that yet. So now we want to find f dot dr dt, and this is the f we just evaluated at r of t. So I'm going to just point and then fill in my dot product. So the I components, 0 times 1. So 0 times 1. J components, t cubed minus t to the 4th times 2t. And then last, t minus t to the 6th times 3t squared. Okay, let's make this look better. 0, this becomes 2t to the 4th, I'm just distributing right here, minus 2t to the 5th, and then back here, distribute also, plus 3t cubed minus 3t to the 8th. Okay, so this is going to be our integrand when we evaluate our work integral. Now, the only thing I haven't done yet is I need a lower and upper bound for my integral, and I wasn't explicitly told t goes from this number to this number. I'm told on my path the points I'm at. And so this one's pretty nice actually. So from the origin, we're just sort of doing like a side step of work right now. The origin is 0, 0, 0. And if we look back at our path, which I erased, but let's write that down really quick. It was r of t equal ti plus t squared j plus t cubed k. How do I get 0, 0, 0 as my output? Well, if these were all zeros to begin with, that's my point. So then this point happens when we have r of 0, which means our starting t value is 0. This one's pretty nice, it's just 0, 0, 0, t is 0. It's not always a coincidence that t equals our numbers at our point, but this time it is. Our ending point on our curve is 1, 1, 1. Same thing, look at our equation, and what would my t values be to get this output? It would have to be 1, 1, and 1. So this is r of 1, so t stops at 1. Alright, like I said, it's not always just the same thing as the numbers you're seeing, it's just sort of a coincidence here that's what we're getting out. So now we're ready for our integration. So our last step here is that our work is the integral from a to b, which is our first t value to our second t value, of f dot dr, which we already did all the work for that. So 2t to the 4th minus 2t to the 5th plus 3t cubed minus 3t to the 8th, all dt. And then this one's really nice, just use your power rule for integration. I'll skip that step and we'll just go to what we get. We're going to get 2/5 minus 1/3 plus 3/4 minus 1/3 for a total of 29/60. So that's the work required to move our object from the point 0, 0, 0 to the point 1, 1, 1 along that curve in space, the work done by the force field. Alright, let's continue, and this time we're going to now talk about flow. So calculations are going to be very, very similar. The flow integrals and circulation for velocity fields. So let me give you this definition first. For a velocity field F over a region containing a smooth curve C, which is parameterized as R of t, the flow along that curve from some point to some point, so from, notice that you're evaluating your curve at A, so like the starting t value is little a, and then you're ending at little b, so R of little b. So the flow along the curve between these 2 points is, your flow equals your line integral again. So the calculation is the ones we've already been doing, it's just now we're describing it as flow when F represents a velocity field and we know we're talking about, or that we're talking about like some kind of flowing, maybe water or something like that. So a note for you, if the curve starts and ends at the same point, so A equals B, then we say circulation instead of flow. So if your curve, you go along your curve and you end where you started, we call that circulation. So let's look at an example of this one. So our example here, we're going to find the circulation of the field F equals x minus y I plus xj around the circle with radius 1 centered at the origin. Okay, so right away, because it says circulation, we know that we're actually starting and stopping at the same point. And the fact that it's a circle, we're just traveling around the circle. So on this one, notice no parameterization of a curve is given, but we are told it's a circle, we're told the radius, we're told where it's centered. So we should probably just start right there. So I'll say a parameterization of the curve, in our case the curve is the circle, is x, well, I'll do it in all at once, because when I gave it to you as a common parameterization, I separated x and y. I'm going to go ahead and put those together and call it R of t. So our x component would be a, which is our radius 1, so I'll just say 1 cosine t for the I direction. And then our y component, it would be a sine t, but a is 1, so sine t in the j direction. And then we're going around this circle once. We're starting and stopping at the same place because of the circulation. Instead of just saying flow, we're specifically told circulation. And so you just have to think about it. If you have a circle, if you start when t is 0, that's like on the positive x-axis, and then you can travel around counterclockwise, and then you'll stop at when t is 2 pi for this parameterization to get you back at that starting point. So that's our parameterized curve, and now we can jump right into the calculations, very similar to what we already did for the last one. We're going to start by finding our field evaluated at our curve. So f of r of t, and this time I'll kind of just point to it. So our x here is cosine t, our y is sine of t. So when I plug them into f, I'm going to get cosine t minus sine t, and that's the I component of f. And then pointing over here, this is our x component, which is just cosine t. So cosine t for j from our field f. So this is f. F of r of t. Okay, the next thing we need to do, just like we did on the last example, is find the derivative of r with respect to t. So just looking right here at r, derivative of cosine, we're going to get negative sine t for I. And then over here, this is going to be cosine t for j. Okay, and then remember what's next. In order to evaluate this integral, in our case the circulation integral, we're going to do the dot product of these two. So let's go ahead and do it up here. So the dot product of these two, so I'll just write it really quick, f dot dr dt is what we're doing. So let's point and multiply. And so I'm going to distribute when I multiply right now. So I'm going to say cosine times negative sine. Doesn't matter which way you write it. Maybe I'll be consistent. Let's say cosine first. Negative cosine t sine t. So this times this. I'm distributing as I multiply. And then negative sine times negative sine. So positive sine squared t. And then multiply the j components. Cosine times cosine. So plus cosine squared t. Now if I skipped too much steps, just know what I was doing. I was doing the dot product. Feel free to write those out when you're doing your own work. It was the I component times this I component plus the j component times this j component. Now we can simplify. This is from the Pythagorean identity. This is just 1. So this is 1, and we get 1 minus cosine t sine t. Okay, we are ready to calculate the circulation. So our circulation is equal to our line integral. We're going to say from a to b, our starting and ending t value. So from 0 to 2 pi of this dot product, f dot dr dt. So 1 minus cosine t sine t dt. And then just straightforward integration from here. I think I'm going to have to use u substitution on this one. So let's work this out real quick. I'm going to go ahead and separate this. I'll say that this is integral 0 to 2 pi of just 1 dt minus over here t equals 0 to 2 pi. And then I'm going to use u substitution here. So I'm going to let u equal cosine t. And that means that du would be negative sine t dt, which is nice because everything's already there for my substitution. Here's u, and then here's dt, negative sine, or du, excuse me, negative sine t dt. So then the minus actually right here becomes a plus sign, and this is just u du. Okay, so I just used some quick u substitution for the second term in my integrand. The first term was just a 1. I just pulled it out into its own integral. Alright, almost there. Now we integrate. This is going to be t, evaluated from 0 to 2 pi, plus u squared over 2. But notice I never changed my limits of integration. You can. I'm going to leave it in terms of t, like I did, and just resubstitute. Either way is fine. You could change your limits of integration. I just didn't do that. So I'm going to change this back to cosine t. So my first term is 2 pi minus 0. So I'll just write it in steps. 2 pi minus 0 plus this one here is going to be sine, actually cosine. U is cosine. Cosine squared t over 2 evaluated from 0 to 2 pi. Okay, so this one, let's just move up a little bit. This is cosine of 2 pi quantity squared over 2 minus cosine of 0, not theta, 0 squared over 2, which cosine of 2 pi is 1, so this is 1/2. And then cosine of 0 is also, it's 1/2 squared actually. The top is 1 squared over 2. And then over here this is also 1, so this is minus 1/2. So this whole thing was 0. So 2 pi minus 0 plus 0, final answer 2 pi. Okay, so let me show you a picture of this one. Okay, so notice the vector field here, F. This was our field, and then our curve here is our circle with radius 1, centered at the origin. And so this is basically showing that a fluid that would have this velocity field, this vector field, is circulating in the counterclockwise direction around this circle. So the circulation is positive, and we calculated that it was equal to 2 pi. the last thing we're going to talk about is this idea of flux. So flux across a simple closed, let me add a D here, closed plane curve. So flux, you could think of flux in a couple of ways. Here's one of them. You can think of it as the amount of a vector field that passes through a curve. Another way to think about that is the rate at which fluid is entering or exiting a region, and that region is enclosed by a smooth, simple, closed curve. So it has to do with, you have an enclosed region and then your vector field, which you can kind of picture as like maybe fluid flowing, moving either in or out of that region. Now, simple and closed, for your curve, for it to be simple, it doesn't cross itself. So a simple curve might look like that, or like this. A closed curve starts and ends at the same place. So this could be a closed curve, and so can this one. And so to put those two together, it pretty much looks like this. It can't cross itself and it can't be open. So it's like these two here. Alright, so next, let me give you the formal definition for our flux and the calculation for it, the integral that we need. Okay, so here's our definition. If C is a smooth, simple, closed curve in the domain of a continuous vector field, and here's our vector field, mi plus nj in the plane, and if n, little n, is the outward pointing unit normal vector on C. So real quick, n, we've seen that notation in the past for a unit normal vector. So remember, normal is perpendicular or orthogonal. Then the flux of the field F across the curve C equals the line integral over your curve C of F dotted with n ds. And then the way we're going to evaluate it is actually say the integral over C of m from your vector field dy minus n from the field dx. This comes from this cross product of how you're going to get n. So I'll talk about that in just a minute, but let me explain this notation really fast. So this right here, that symbol, is letting you know about a little bit about the integration, what's happening here on your curve. So this is saying basically that the integration around is going to be around a closed curve in the counterclockwise direction. Counterclockwise direction. So there's a little edge on this, and that's there for a reason. It's letting us know that we're traveling counterclockwise, and then the fact that it's a closed loop is the part for the closed curve. So for n, the way you get n is this unit normal vector. If you think about it, like I said, that's perpendicular or orthogonal. You're going to end up taking the cross product of your unit tangent vector with the k direction vector, your vector along the z-axis, or in the z direction, excuse me, your unit vector in that direction. So let me show you what that looks like. So to find an outward unit normal vector, which we're calling n, for a smooth curve C in the xy plane that's traversed counterclockwise, and that's when t increases, we're going to take n to be the cross product of t with k. So remember, k is our principal unit normal vector in the z direction. And so if you cross those two, notice t right here, this is the counterclockwise rotation or orientation. T is tangent to our curve at that point, and it's pointing in the direction of travel. K is perpendicular to it, pointing in the vertical direction, and then the cross product of those two is what n would be, and it's this outward unit normal vector. If we're doing clockwise motion along our curve, so clockwise motion, notice k is still pointing the same way, but t points in the direction of travel, so it's actually pointing the other way from this image over here. And so when we cross to get n, do the cross product now, we're going to cross k with t. So just change that direction, and that's going to give us this outward unit normal vector n. Okay, so a quick note, for any smooth parameterization where x is g of t, y is h of t, and then t is between a and b, that traces our curve c exactly once, we can use this form of our integral. So we're going to be able to do that now. So let's try out an example, and so what I want you to notice is that everything's pretty much just like our last example. We're just calculating something different now. So find the flux this time of your field f equals x minus y I plus xj, so that was from the previous example, that field, across the circle x squared plus y squared equals 1 in the xy plane. That was also from the previous example, so that was our circle that we parameterized. So notice the parameterization that we've already used for this circle, x equals cosine t, y equals sine t, t goes from 0 to 2 pi. This is going to work out this time for us to be able to evaluate our integral here for flux, because it traces our curve in the counterclockwise direction exactly once. We go around that circle counterclockwise exactly once if we use x and y equal to cosine and sine, and we start at t is 0 and we stop at t equals 2 pi. So let's fill in what we need, or figure out what we need to use this integral. We're going to need m, dy, n, and dx. So let's work on each of those at a time, and then we'll put it together in our integrand. So first, we have what x is, we have what y is. So m is from our field here, our vector field. So mi plus nj. So this is m. So x minus y, but we're going to write it in terms of our curve, in terms of t, essentially. In the past we called this r. So in terms of our curve r. So this is going to be cosine t minus sine t. Okay, next let's find n. So this is n from our field, and n is just x, which is just cosine t. Next we need a dx, because all this is going to go into our integral. Dx is the derivative of x with respect to t. So the derivative of cosine with respect to t is negative sine, and then I need my dt here. Last, we need dy, which is the derivative of y with respect to t, so that's going to be cosine t dt. And now we're ready to fill in our integral. We're going to put this all together. So our flux equals, let me write it again, our integral over our closed curve in the counterclockwise direction equal to m dy minus n dx. So that equals the integral from 0 to 2 pi, which was our t values, m, which is cosine t minus sine t. I might run out of room here. Let's squeeze it in. dy. So dy is cosine t dt. We're going to take that dt and put it all the way in the back. So cosine t here. So let me just check off what I've used so far so you know where we're at. So we used both of those. Now minus n, which is cosine t, dx, which is negative sine t, and then the dt is going to go in the back. So negative sine t, and then we save that dt for the end over here, and so we use both of those as well now. Okay, and then this is going to give us our flux. So let's simplify and then do this integration. Okay, so I'm going to distribute right here, and so we get integral from 0 to 2 pi cosine squared t minus sine t cosine t. I'm just distributing right here. And then minus, right here, this becomes actually a plus, cosine t times sine t dt. Oh, look at that. These two add up to 0, so this all becomes integral of just cosine squared t dt. And then this one, you have to just remember from trig what you need in order to evaluate this. So from trig, one of your double angle formulas will help here. So from trig we know that cosine squared theta equaled 1 plus cosine 2 theta over 2. So we're going to substitute that in here to evaluate our integral. So from 0 to 2 pi, I'm going to go ahead and separate this fraction here and say that this is 1/2 plus 1/2 cosine 2t dt. I just am going to do a quick u substitution. You might be able to do this one in your head, but I want to write it out real quick. So this is 2t for u right there. And then that means my du is 2 dt, which means I'm going to end up dividing by 1/2, or dividing by 2. So 1/2 du replaces dt. So we have, and we'll kind of do it all at once. Well, I won't skip any steps. I was going to jump into the next one, but we'll go through it. So we have 1/2 plus 1/2. This is going to be cosine of u. Well, I should technically change my limits, or let me just put it like this. Make it very clear. This is still t. U times 1/2 du. Okay, so let's go ahead and evaluate. Integral of 1/2 is 1/2 t. So technically this is still dt. I sort of mixed things together here. Hopefully it's not too crazy looking. So 1/2 t plus, this becomes a 1/4. Integral of cosine is sine, and let's go ahead and plug back in what u was. It was 2t, and we're evaluating from 0 to 2 pi. There we go. This is the nicer version. It got a little crazy looking right there. Almost there. Let's keep going. Plug this in. Plug in a 2 pi right here. We're going to get pi. Then plug in a 2 pi here. We're going to get, oh, this is a 1/4, sorry. 1/4 from there. So we're going to get plus 1/4 sine of 4 pi. And then minus, this becomes 0. 1/2 times 0 minus 1/4 sine of 0. Okay, this is 0. This is 0. So final answer, pi. So all that to get to just pi right there. So our flux of this field across that circle, x squared plus y squared is 1, is just equal to pi. Now, because it's positive, let me just give you one last note here. That tells us about the net flux and that it's going to be outward. So note, if your flux is positive, so positive flux implies, let's get rid of this, that the net flow across the curve is outward. And then the exact opposite is true for negative. So if you have a negative flux, when you do this calculation, negative flux means that the net flow across your curve is inward. The curve is inward. All right, there it is. Okay, so we talked about work, flow and circulation, and now flux. So just a number of things that we can do with our vector fields and our line integrals. That's it, you guys. Thanks for watching.